In this video, we will talk about functions. It is a different view than you are perhaps used to from algebra. It is a set theoretic view and one that continues our discussion about relations. So this video has two overview slides. This one here, that is a lot of it is actually different diagrams. And you'll see going over the concepts on this slide will go fairly quickly. And this second slide here with examples and diagrams as well. We will start with the definition of a function. So a function from a set A to a set B is a non-empty relation that satisfies two conditions. One, existence. That is, for all elements A in the set A, there's going to exist a B in the set B such that AB is a member of the function. And two, uniqueness. If AB is in the function and AC is in the function, then necessarily B equals C. That is, for every element A in A, there is exactly one. That is, there is one and only one element B, such that AB is in F. This definition should be totally consistent with what you know from algebra. That is, every element A in the set A gets mapped to exactly one value, B, from set B. Set A is called the domain of F, sometimes abbreviated domain of F, and set B is called the codomain of F. The range of F, denoted RNF, is a set of all elements of F such that B is in the set B, such that there exists an A in the set A such that AB is an element of F. So the codomain is what that is valid to be mapped to, and the range are the specific values that have something mapped to it. We use this notation. F is a function going from set A to B. Also, xy is a member of F. We often say that F maps x onto y, or y is the image of x under F, and we write y is equal to f of x. Again, this should all be consistent with what you learned from algebra. Now our next example. So if A is equal to 1, 2, 3, and B is equal to 2, 4, 6, 8, when we define a function f, and I'm just going to kind of make some notes here, that goes from A to B, what I need to do is make sure that the numbers 1, 2, and 3 appear exactly once as the first element of an ordered pair. And after that, I can define two functions. So just randomly choosing from B, one of these four elements from B to pair with 1, I might choose 6. To pair with 2, I might choose 6. And to pair with 3, I might choose 2, just random. This would be a function. And this would also be a function. I have something paired with 1, 2, and 3. And again, each of these elements in A appears exactly once as the first element of an ordered pair in both of these. So these are both functions from A to B. If I look at this next function, or next relation, it is not a function since 2, f of 2, maps to both 6 and 8. And that can't happen because for every element of A, there's one and only one element of B, and that is in AB. And here I have 2 as an element of A, but here I have 2 elements of B mapped to it. So this relation is not well defined, and being not well defined is what keeps it from being a function. And I wrote that right here. So this relation is not well defined and it keeps it from being a function. Next we have this relation, 1, 4, and 3, 8. And this is also not a function because f of t2 is not defined at all. So this relation is also not a function. And from algebra, you know that once you graph a function, the function should pass a vertical line test. In other words, you should be able to draw any vertical line. So if I draw some vertical line maybe here, you can see that the function only crosses that vertical line once. And here's another vertical line, it only crosses the function once. If we had something like this for f of x, and I drew a vertical line, you can see this does not pass the vertical line test because there are 2 points the same value of x gets mapped to two different points. So this is not a function here because it's not well defined. Our next definition is of surjective and injective functions. So a function f is called surjective, or also called onto, if b is equal to the range of f. In other words, it's surjective if every element of the set B has something mapped to it. A function f from a to b is called injective, or one-to-one, if for all a and a prime in the set A, f of a equals f of a prime implies that a equals a prime. And a function is called bijective if it is both surjective and injective. And we'll do some pictures to kind of illustrate this. We'll start with this blob. This is the common diagram. This blob represents the set A, and here I have one element in it with little a. This blob represents the set B, and I have one element, little b, here. And F is a mapping from the set A to B, so we have this arrow going from A to B. And in particular, F maps the element little a over to the element little b. And now we'll use this style of diagram to illustrate one-to-one and onto, or injective and surjective functions. And I'm used to saying onto and one-to-one. So here's our diagram, our general diagram. Then this diagram is not one-to-one because here I have two elements from A mapping to the same element of B. And if it's one-to-one, if f of a equals f of b, that would mean a is equal to a prime. But here I have two distinct elements of a mapping to one. So it's not one-to-one, and it's not onto. And it's not onto because there is this element here in b that is not mapped. In other words, b is not equal to the range of f because I do have something here in b that is nothing from a maps to it. Here I have a function that is one-to-one, but it is not onto. It's one-to-one because we don't have two things mapping to the same element b. It is not onto because, again, we still have this element here in b that nothing is mapped to. This one is onto and not one-to-one. So it's onto because you see there's two elements in b, and they both have something mapped from a that maps to it. So it's onto, but it's not one-to-one because you have this element here that is mapped to from this element in A and also this element in A. So this makes it not one-to-one. And here is one-to-one and onto. So it's onto because you can see there are three elements in B and they all have something mapped to it. And you can also see it's one-to-one because there's nothing in B that has two different elements of A mapped to it. Here is an example with numbers and equations and things. So you're familiar with the function f of x is equal to x squared. And here I have the graph. Looking at our terms, we would say that f goes from the real numbers to the real numbers. So the real numbers is our domain, or x is our domain. And also the real numbers for y is our codomain. Our range then would be the numbers that actually get mapped to. So those are, the range would be the positive real numbers. Let's see what we have. So here f maps from R to R. F is not surjective. It is not onto because there's no real number that maps to -1. In fact, nothing maps to the negative numbers. If we took the codomain to be 0 to infinity, positive infinity, then we could say that it is subjective. But in here, we had already specified that f goes from real numbers to real numbers. We did not limit to the only positive. So with this kind of codomain, it would not be surjective. It is also not one-to-one because we have f of 2 is equal to 4 and f of -2 is equal to 4, but obviously 2 does not equal to -2. So here again we have f of 2 is equal to f of -2, but we don't have this condition here where 2 is equal to -2. So it's this is a function. It is neither surjective nor is it one-to-one. Our next example is a function called the characteristic function or indicator function, and we'll see why it's called that in a minute. But let A be a non-empty set and let S be a subset of A. We define the function x of S is maps from A, elements of set A, into the codomain of 0, 1, and it maps it this way. It's 1 if A is an element of S, and it's 0 if A is not an element of S. So first, let's just kind of do a little example so we can kind of get a feel of what this is. And I want to kind of create a little example because when I look at this definition, it really doesn't do much for me. In other words, there's nothing that intuitively says to me, oh yeah, I get what this function is doing or what this description is trying to say. And if you're in the same boat, the thing to do is to look at each part of the definition in small pieces. So we'll start by looking at A is a non-empty set. So I made a little set A here, and I let S be a subset of A. So here's my A, here's my subset of A. And next, my function x of S, so my function is dependent on my subset S. It maps from A, so it takes these elements, 1, 2, 3, 4, and 5, and it will map it either to 0 or 1, according to this rule. So if I look at xs of 1, I can see that 1 is an element of my subset, so it gets mapped to 1. 2 is also an element, 2 is the next element of A, is also an element of my subset, so it gets mapped to 1. And 3 is also in my subset, so it gets mapped to 1. The element 4, however, is not in my subset, so it gets mapped to 0. And the element 5 in A is not in my subset, so it gets mapped to 0. So I can see now why it's called the characteristic function or indicator function. It indicates for my set A whether or not it is in my subset. If it is, it's a 1, and if it's not, it's a 0. It's funny because now when I look at this definition, it seems quite obvious what it does. But that's because I'm used to it now. And in fact, a lot of times when you have things that are an indicator function where you map to 0 or 1, the 1 tells you what you're looking for, is A an element of S. And the 0 tells you when that criteria has failed. So that's a very common kind of thing. But I will also say if you ever get stuck on a definition like this and you it's never a mistake to try to make a little small concrete example of A and S and then plug it in, and then hopefully you'll get some insight. Now that I have a better understanding of what this function is, I can ask, is it onto and is it one-to-one? So first, I can look at this example and I can see that it is onto because I have hit everything here, 0 and 1 in my set that I'm mapping to. Is there any way that I might not hit 0 and 1? Is there any way that it's not onto? And the answer is yes. Because if S, and now I have my subset S1, is exactly equal to A, then everything in A will map to 1 because everything in A is in my S1. Another way that we can have something that is not onto is if S2 is the empty set, because now everything in A, since none of them are in S2, will map to 0. So in this way, the number 1 will never get mapped to. So these are two examples where x of S is not surjective, it is not onto. We can also see x sub S is not one-to-one. Just from our last example where A is equal to 1, 2, 3, 4, 5 and S is equal to 1, 2, 3, we can see x of 1 and x of 2 are both equal to 1, but 1 does not equal to 2. Looking to see where we are in our overview sheet, we defined a function from set A to B. We said that the set A is called the domain and the set B is called the codomain, and the range of F are the values of B that actually have an A, some element of A mapped to them. We also looked at different ways of expressing the notations, and there was a note. We looked at f of x is equal to x squared, and then we also considered where g of x is equal to x squared. And one thing I didn't say is these are actually two different functions because this function here maps from R, the real numbers, to the real numbers, Whereas this function g of x, we limited the codomain from 0 to infinity. So actually, by having a different codomain, they are considered two different functions. We looked at other examples of functions. We looked at the graph, the vertical line test of a function. So if you pass a vertical line anywhere along this graph, it should only touch the function once if it is a function. Otherwise, it's just a relation. We talked about onto and one-to-one functions, and we did these pictures here to illustrate that, as well as the example of f of x squared and one other example, the indicator function. Now we're ready to go on to the second slide. And we'll start with talking about images and pre-images. So if we have a function f going from a to b, so here we have a set A, we have a set B, and f maps things from a to b. If C is a subset of A, so here I have a subset of A that I call C. The set that this C gets mapped over to in B, we're going to denote it with f of the capital letter C. And the capital letter, because this is not just f mapping a member, this is where the set C gets mapped to, and we call this the image of C. So in the definition, we would say C is a subset of A, and we let f of capital C represent the subset of B, such that those are the f of x's, such that we have x coming from set C. Now, if we consider D a subset of B, so here's my subset D, we let this pre-image of D, and it looks like, the notation looks like f inverse of D, and that's not a coincidence. However, it's really important when this D is not an element of B, but is actually a subset of D, that you call this pre-image. There is an important reason for that, and we'll talk about that later. So we let this pre-image of D represent the set X in A such that f of x is in D. So that's the pre-image are the elements in A that get mapped over into the set D. So we have a set C gets mapped into the image of C, which is a subset of B. And if we have a subset of B, D, called D, then the pre-image of D are the elements in A that get mapped over into the subset D. Here I have a quick example of why I feel like it's not important to call this f inverse of D if D is a set. So if x is an element of A, not a subset, but if x is an element, then when you do the inverse of f inverse of f of x, you get back x. However, if C is a subset and you do the pre-image of the image of C, you do not necessarily get back C. Sometimes you do, sometimes you don't. And it is the case, and we'll see this in a few slides, that C is contained in the pre-image of f of C. In summary, the reason why I stress the correct terminology here when we have sets that you call this the pre-image and you don't get lazy and call it the inverse is because if you do, the inverse has properties, and the properties it has do not necessarily carry over to the properties of pre-image. I've come back to this example where we let f be a function from the real numbers to the real numbers, and we define f by f of x is equal to x squared. So I have that graphed here, so you're familiar with this example. First, I'm going to look at the interval 0, 2, including the endpoint. So I map that out here on my x-axis, 0 to 2, that's C1. And then I want to look at the image of C1 so that the values that f maps as x goes from 0 to 2. And these values go from 0 to 4. You can see 0 all the way up to 4. So here is my image. It's 0 to 4. Next, I am going to look at the interval between -1 and 2 on the x-axis, and I want to know what the image is. So those are the values that, and this is actually not drawn very well, this should be 1, that f of x takes as x goes from -1 to 2. So it goes from 1 all the way down to 0, and then back up to 1, and up to 4. So it's essentially 0 to 4. The fact that it goes 1 to 0 is already captured by going from 0 to 1. So the range of values for f of x is 0 to 4. This next problem here, C3, is done as a review problem. Okay, for these 3 examples now, I'm going to let this be D, the subset of B. So it's what gets mapped to. So if D is between 0 and 4, then if we want to find the pre-image of D, then we need to look for the values of f that are between 0 and 4, and we want to find the values of x that map between 0 and 4. So we're looking at this portion of the graph, nothing up here, and the values of x that map between f to 0 and 4 are the values of x between -2 and 2. So that is our pre-image. Next, if we want to look at D, is our values -5 to 4. I had to kind of extend my y-axis here. So where does x take the values? What values of x will give us y values between -5 and 4? And actually, no value of x gives us any negative values, so we're stuck above the axis. And to go from 0 to 4, that's actually the same as the other problem. So if we're looking which values of x will give us values between here and here, and actually it's really just 0, you can see that those are the same x values, -2 to 2. This third problem here is also saved as a review problem. Here is our next example. We have a function that goes from the real numbers to the real numbers given by f of x is equal to sine of x. So we want to find the following sets. The first thing to notice is this is f of a set. It is not like f of 0, which is equal to sine of 0, right? And it's not something like f of pi, which is equal to sine of pi. This is f of a set. So in other words, you want to realize when you get something like this, you're asking what is the image of 0 to pi under the mapping f. So here is C, which is a subset of my real numbers, and I want to know what the image is, f of C. So here is my subset of my domain from 0 to pi. I want to know what the image is. Well, here f of 0 to pi goes from 0 to 1. Next, I want my image of 0 to 8 pi. So as you know, here we go to 2 pi, 3 pi, it just cycles through. So essentially, you're going through all the values that sine will take, which is -1 to +1. This last problem is a little bit different because of this inverse or pre-image. So it's asked, so this part here, the -pi to pi, is now not in your domain, it is in your codomain. So in other words, this is asking if in my codomain, I am looking between -pi and pi, I want to know what the pre-image, what are the values of x that map to something between -pi and pi. And that would be all the values, all the real numbers. So I included this note here that in this point, because we have this inverse, we're looking at a pre-image, that means this is the codomain, and we want to know, so it's over here, it's like this D. We want to know what is the pre-image of -pi to pi. In other words, what are the values over here that will map that our function will map to something between -pi to pi. And one last note, because sine only goes between -1 and 1, this is the same pre-image. The -pi to pi is the same pre-image as -1 to 1. So something you have to be careful about this pre-image. So let's say you have a function going from A to B. So there are many relations that hold between the images and pre-images. Okay, that's fine. So if we map C onto f of C, so f of C is the image of C. But now if we want to look at the pre-image of f of C, do we always end up with C again? And in general, the answer is no. So let's take a look at this. So this mapping, there would be no problem. You could go from C, you could look at the image, f of C, and then when you look at the pre-image of f of C, you'll get back C. But now the problem is there might be other elements in A that also map to f of C, the image of C. So in other words, if, say, this element 3 also gets mapped to A, now we have the image of C is equal to AB. So when we map back, the pre-image of f of C is now equal to 1, 2, and 3. So it is not equal to C. However, this pre-image of f of C will always contain C, as you can see here. To expand on the idea that we had talked about here, there's this theorem here. With f is a mapping from A to B, let C, C1, and C2 be subsets of A, and let D, D1, and D2 be subsets of B. Then the following hold here. And A is exactly the situation we were talking about before. And this here is the picture we had looked at for part A when we were discussing it in this discussion here. And the way that I come up with this picture, and again, this is one of those things when I read the theorem, I read this description, it really doesn't mean a lot to me. And in fact, the fact that, if anything, that there's not an equals is not immediately apparent to me, because it seems like if you take f of C and then you take the inverse, because I'm reading this as inverse as opposed to pre-image, it seems like you should be equal to C. And to be quite honest, I'm just going to kind of walk you through my thinking of how I got this picture, is I did start out with a set C, and I put just one or two elements in, you don't want to overdo it, and then I did make an image f of C, and I mapped it to AB, and you could have mapped it to 3, 4, whatever. I just decided I want to use letters here and numbers here. And then I thought, okay, well, if I then take the pre-image of f of C, I'm obviously going to get back C. So somehow this seems like it should be an equality. But this theorem seems to think that C is contained in the pre-image. In other words, it thinks that this C here is a subset of the pre-image. So I am going to start by adding something to my picture. Since C is a subset, that must be there's some other element out here. And then, since we want this 3 to be in the pre-image, you might be tempted to add something like this, C over here. But that's not right, because this set here is supposed to be f of C, and 3 is not in C, so we have to take that away. And then maybe we're tempted to add something over here, an element D. Maybe it goes like this, but that wouldn't work either, because now when I map the pre-image, I still get back to C. So really what's missing is the possibility, again, we want 3 to be in the pre-image of C, so it's probably something that looks like this, where 3 and 1 both map to A. So that way the pre-image of C gets mapped back correctly to 1, 2, and 3. So that's the drawing we have over here. So I did these drawings just to get a feel for what these theorems are saying, but by no means are these kind of diagrams proofs. So that is what we will do next. And again, I didn't do diagrams for E, F, and G. I will leave that to you. We will start with the proof of part A, which is kind of easy because it's a subset, so there's only one direction to prove. We start with X being an element of C. We want to show it's an element of the pre-image of f of C. Well, if X is in C, then f of X is going to be in the image of C. Then if we look at the definition of pre-image, which we have over here, then by definition, I just rewrote the definition of pre-image of C. That's going to be all the elements X in A, again, because we're starting at set A, and C, C1, C2 are subsets of A. So all the X in A such that f of X is in f of C. And again, I'm just mirroring the definition here of what it is to be in the pre-image. And since f of X is in f of C, that must mean that X is in the pre-image of f of C. I am also going to look at A and formally prove that this is not an equality, and I'm going to do that by showing that this right-hand side is not a subset of the left-hand side. If we recall, I used this drawing to explain why it was not the case, and the idea is that there were things that mapped to f of C that were outside of C. To do the proof, I altered my example and I kind of stripped it down because I had some extra stuff here. So for example, to do this proof, I really didn't need two elements inside the subset C. To go to f of C, I really only needed one. So I replaced C with C1 here that has one element that goes to f of C1. And then I needed something for this proof outside of C. So I made that element number 2, which is in C2, and that also goes to f of C2. So 1 goes to A, 2 goes to A. So f of C1 is equal to f of C2. They both go to A. So I look at f of C1 is equal to f of C2, but C1 and C2 are disjoint, as you can see. If I look at f of C1, that is over here, it's A, and the pre-image of A is equal to C1 union C2. So you can see here that the pre-image of f of C1, of the image of C1, is not equal to C1. Because this video was getting long, I did not do all of these proofs, but I do have part C and part F as a review problem with solutions at the end of this video. Next, we'll talk about composition of functions. So if we have functions f and g, where f goes from set A to B. So here I have the set A to B, f maps from A to B. And g goes from B to C. So here I have a set C, and g goes from set B to set C. Then for any element A in set A, f of A is in B. So g can be applied to f of A, which yields g of f of A, which is an element of C. The function composition gives a correspondence between the element A in set A and the element g of f of A in set C. In other words, it's a mapping, essentially a mapping from A to C. Our first example, find an example to show that the composition of two functions need not be commutative. In other words, we're trying to find a functions f and g such that f of g of x does not equal to g of f of x, which doesn't seem that hard because there's no, if you start with f of x and then map to g, it's not necessarily true. You can map back g to f of x. And in fact, here's my first example. I say f of x is equal to x squared and g of x is equal to x plus 1. So when I plug in f of g of x, so I plug in g of x into f, and I get x plus 1 squared. I can do that in the other order, and I can plug f of x into g and get x squared plus 1. And you can see these are not equal. I can also do this other example, which is even more extreme. I have f maps 1 to 2, and then it maps 2 to 2. And g, I can have 2 mapping to 3. So I can plug in, I'll do this one first, g of f of 2. So I plug in f of 2. So f maps 2 to 2 into g, and I get g maps 2 to 3. However, if I plug in f of g of 2, here I have g of 2 maps to 3, so f of 3 is not even defined. So they're definitely not equal. So we have this following nice theorem, and I say it's nice because everything behaves as if you want it to. So if f is a function from A to B and g is a function from B to C, then if f and g are surjective, then g of f of x is also surjective. In other words, the function composition is also surjective. And if f and g are injective, then the function composition is also injective. And if f and g are bijective, then the function composition is bijective. So everything behaves as you would like, and we can do a proof. We will do proof of part A. So f and g are surjective. To show something is surjective, we need to show for all y and c here that there exists an x in A such that g of f of x is equal to y. In other words, everything in C is hit. And we'll start by considering y and c. Now, since g is surjective, so y is over here in C, but since g is surjective, there exists some x prime in B such that g of x prime is equal to y. So that's just the definition of surjective. And then since f is surjective, there exists some x in A, then that maps to x prime. And that's the end of our proof that g of f of x is surjective. We have found an x in A that maps to x prime in B, and that x prime in B will map to y in C. And I believe our last topic is inverse. So if we have a function from A to B and it is bijective, it's 1-to-1 and onto, then the inverse function, and now because we're talking about a function and how it operates on individual members of a set, so we'll call this f inverse, is given by yx in B cross A when xy is in F. And a quick example so you can see why this is, you just swap the x and y. Let's say A is equal to 1, 2, and B is equal to 3, 4. A cross B are all the possible ordered pairs where you take A as the first element of the ordered pair. So here is where I take 1 to be the first of the ordered pair, and then I combine it with every element in B. Here I take 2 as the first of an ordered pair, and I combine it with every element in B. And now a function is just any subset of A cross B, but it only has 1 appearing once as the first element of an ordered pair in my function, and then 2 appears once as the first element of my ordered pair. So I'm going to take this function here. And actually, these 3 functions here are also valid. Those are all the functions you can get out of A and B. So f is the function that maps 1 to 3, and it maps the number 2 to 4. So I mapped 1 to 3, 2 to 4. So by this theorem, my f inverse, not theorem, but by this definition, my f inverse is equal to 3, 1 and 4, 2. I just swapped the x's and y's. And you can see this definition gives you your intuitive notion of inverse from algebra, because if I take f inverse, f of 1, that would be equal to f inverse. So f maps 1 to 3, so f inverse of 3 would get you back to 1. So f inverse of f of x equals x. And you can also verify that for 2. F inverse of f of 2, so f of 2, 2 maps to 4. F inverse of 4 maps back to 2. And you can see how that works. And our first example is if we define f from 0 to infinity by the formula f of x is equal to x squared. Since f is not injective, f does not have an inverse. And we can see that f of 3 is equal to f of negative 3 is equal to 9. So when we map 3 and negative 3 to 9, the inverse, we don't know where to map 9 to. It's not well defined because it really should map to 2 different numbers, but that's not the way functions work. You only map it to one number. However, if we restrict the domain of f from 0 to infinity, then the function is injective and surjective, and thus we can have an inverse, which is the positive square root function. And then there's this theorem that combines both the ideas of function composition as well as inverses. So if f goes from A to B and g goes from B to C, so we can have this function composition, g of f of x, which goes from A to C. If f and g are bijective, then our function composition is bijective by a previous theorem, and g of f of x inverse is equal to f inverse g inverse of x. And here's the picture. We have f goes from A to B, g goes from B to C, our c inverse goes from C to B, and our f inverse goes from B to A. or we could have this function composition, g of f of x. And now you can see our inverse, though, has to happen backwards. So if you're over here at C and you want to get back to A in the inverse direction, first you have to apply G inverse on X to get back to B, and then you can apply F inverse. Our last theorem, suppose F goes from A to B, C, C1, C2 are subsets of A, and D is a subset of B. Then the following hold. If F is injective, then F pre-image of f of C is equal to C, and if f is surjective, then f of the pre-image of D is equal to D. And if f is injective, then f of C1 intersect C2 equals f of C1 intersect f of C2. So this might sound familiar. It certainly starts out a lot like one of our previous theorems, where we said that the pre-image of the image was not necessarily equal to C, but it would always be contained in C, or C would be contained in the pre-image of the image. And we had done a drawing that explained why that it wasn't necessarily equal, and that was because here, if C is equal to the set 1, 2, then we can have the image of 1, 2 might go to A and B. But there could be things outside of our set C that also maps to the image of C. In other words, here, this 3 could map to the image of C, in which case, when we take f of C, we get this image here, AB, and then when we go back to the pre-image, we might get an additional element, which is why C was the subset. In this case, if f is injective, if it's 1 to 1, then we're never going to have this case where something else maps to A. So this case would not be possible, in which case we can have the equality here. Similar for B and part C. And here is the formal proof if you would like to take a look at it. We've now covered the main topics of this video. In the next slide, I'll have some review problems for you. I have these 3 review problems, although 1 and 2 have 2 parts to them each, so it's sort of like 5 problems. Give them pause the video, give them a try, and on the next slides, I'll have solutions for you. Here are the solutions to problem 1. These are the 2 proofs and some drawings to go with problem number 2. And here's the solution to the last review problem. And that is it for this video. Thank you for watching.